Our next speaker is Ms. Rita Kesrouani. Rita is a data analyst with JP Morgan. She's our own AUB graduate from the School of Engineering. She discovered her passion for applied mathematics and innovation. Rita will highlight how she has been applying data analytics for risk management practice and automating time-consuming processes, leveraging machine learning at JP Morgan. So I will leave the floor for Rita.
Hi everyone, I'm very honored to be speaking at AUB today. So as a quick introduction, my name is Rita. I graduated from AUB a few years ago with a big interest in applied mathematics and data analytics. So I decided to move to New York and pursue a master's in operations research at Columbia University. And after that, I joined a data analytics team at JP Morgan, where we use huge amounts of data in order to gather insights and drive decisions for senior management levels. So my team is called Mirna? Sorry, where's Mirna? I think the screen is not working. Fida?
Can Hani help us? Okay, great. Here comes the savior.
Oh, thank you.
What's your name?
Rita Kesrouani.
Rita?
Yes.
Okay. Okay.
Thank you. Thank you very much. I'm sorry about that. So my team is called Wholesale Credit Analytics and Solution. We call it WCAS. So let me explain a bit what it means. Wholesale banking is basically the practice of lending and borrowing between very large institutions. So if we take the example of Apple, if Apple wants to finance its new technology, for example, it would go to the investment bank of JP Morgan to get a loan from there, and the investment bank is part of the wholesale bank. So what WCAS does, WCAS exclusively owns the wholesale portfolio data of JP Morgan, which contains all the information about the traditional credit products, such as the loans, that were owned by JP Morgan across history. And we use this data in order to perform analytics, to understand historical wholesale portfolio behavior, to investigate risk mitigation strategies, and to support decision-making and portfolio management. WCAS is subdivided in many teams, as listed here on the slide, but now I'm going to focus only on my sub-team, Portfolio Analytics and Solution, and how we use data in order to gather insights. First, I'd like to give you a little bit of context about risk management in general. Banks carry many types of risk, and the main types are market risk, credit risk, and operational risk. WCAS focuses only on credit risk, which is the risk of a borrower not being able to make a required repayments on its loan. And also, some institutions, such as JP Morgan, are so large and so interconnected with one another that their failure can be disastrous to the economy. We call these institutions too big to fail. In order for these institutions to protect themselves from the risk they carry, and more importantly, to prevent an economic disaster, they need to have enough capital in their balance sheets. So to make it simpler, let's look on the slide at Bank A on the left. Bank A has much more debt than assets. It means that it owes much more money than what it owns. And if we take a closer look to the loans under the assets, the loan box represents the amount of money Bank A expects from its borrowers to return. So if a borrower is not able to make a required repayment, this loan box will become smaller and the gap between that and assets even larger. In that case, the bank would go bankrupt, and in worst cases, it would become insolvent and would not be able to give you back your money if you deposited money there. So to prevent that, you need enough capital in your balance sheet. And if we look at Bank B has much more assets than debts. So the difference is called the capital. If a borrower at Bank B is not able to make a required repayment, the loan box will become smaller, but the capital will stay positive and will serve as a buffer that will absorb the unexpected losses. After the financial crisis, many regulations were imposed to banks and forced them to have very high levels of capital to keep them safer. And obviously, although this keeps them safer, is it really good for banks to have very high levels of capital? Banks make a significant part of their revenue from interest income, which comes from lending money. So keeping too much capital in their balance sheet without investing it or lending it will significantly affect their profit. But on the other hand, having too low levels of capital will significantly increase their risk of going into distress. So for this reason, we want to find a way to compute the most accurate value of capital without being either too conservative or too risky. And to be able to do that, we want to be able to estimate the loss the bank will experience in the future. So the expected loss due to credit risk can be computed using a very simple formula, as stated on the slide here. So it's the probability of default times the loss given default and times the exposure of default. However, being able to compute the inputs to this equation requires enormous amounts of data, and actually a lot of components goes into the equation, such as the collateral owned, the client rating, the loan type, etc. And a bank that doesn't have any data will not be able to have a very strong model for their capital, and they will be forced to use standardized regulatory techniques to compute their capital, which is way too conservative and hence unprofitable. And this is where we see the value of data in a bank. Here, I tried to make a simple illustration of our data. So each column here would comprise of a specific feature, for example, client ID, date, credit rating, which is a key indicator of the risk of a client, geography, default, etc. We have many more features. We have in total around 160 features and around 180 million rows. So what exactly do we do with this data? First, we try to improve our techniques in computing the capital, as I mentioned before, but also we try to answer questions that businesses have, such as, for example, what industries are more risky than others? What are the ones that are growing faster than others? And finally, an aspect that I really like about our data is that it's a way to store the past into a big table and to really learn from the past mistakes that were done in the recessions and try to ensure it's never going to occur again. Now I'd like to walk you very quickly through the 6 main steps of our analytical techniques. And I have on the right, as an illustration, our rating methodology. So here I want to show you how we use the historical rating of our clients to try to predict or to give a rating to a new client that comes into JP Morgan. So the first step here would be to gather the data you need to answer your question. In the case of the ratings, we have historical ratings, companies' financials such as their sales, their interest expense, their debts, etc. We also have their default history. Second, we want to clean the data, which is the most time-consuming part in the whole process. We have a lot of missing values, error, format conflicts that we need to solve. And finally, the third step would be to do some feature engineering, which is a very exciting part, where you use the actual feature you have in your data to create new ones that will make you able to draw faster conclusions. Next, when you have your data clean and ready, you want to now create your model. So the first step now would be to split your data into 2 sets, a train set and a test set. You will use the train set to create your model, and the test set, you will keep it until the very end to test the model you created. Next, you want to visualize and understand your data. You want to understand the correlation between your features, the relationship, in order to be able to interpret correctly your model and to choose the best way to create your model. In the case of the rating, we chose a very simple approach, which most of us know, which is the linear regression. We found a linear relationship between the ratings of our clients and their financials. Lastly, we want to assess our model. So we will take our test set and compare the actual ratings of our client against the predicted ratings of our clients using the model we just created. So I walked you very quickly through the 6 main steps of our analytical techniques. Now I want to show you how we use these steps and these techniques in more complex problems. And I wanted to end my presentation with a very exciting project that my team has been working on for almost a year and a half. So basically, when JP Morgan enters a deal with a client, they need to write a credit agreement, which is a document that will have all the information about the deal, such as the restriction to the deal, the pricing metrics, etc. This document has on average 300 pages. It takes an experienced lawyer almost a full day to skim through it and pull out the relevant data points. It also takes a few months to train someone to read this document and to be able to interpret the document. And on the slide here, this standard flow is shown as the red line here, which is based only on human processing. So what my team did, it collaborated with another team to create a new software called Contract Intelligence, or COIN, that will basically do this job in a few minutes. It will ingest the document, process it by breaking it down into many categories. It will extract the data points from each of these categories, and finally put it as a summary on the display screen. So I showed you how what COIN does. Now I want to show you how it learned to do it. So COIN learns by reading massive amounts of text and memorizing which words tend to appear in similar contexts. So as I said before, so let's say here, to make it simpler, we want to predict if a document has positive or negative covenants. And covenants means terms and conditions of credit agreement. So I will take a bunch of labeled documents that are labeled as positive and negative. I will count them, and by reading them, I can see the frequency of words appearing in each type of document. And by doing this, I'm finally able to compute probabilities of finding a specific word in a specific type of document. Now that I computed these probabilities, I want to use these probabilities in order to predict, using a new document, if this document is positive or negative. So I take a new document, and by reading it and looking at the words that are in it, I can find the probability of this document being positive or negative. And finally, I can classify it as being positive or negative. And the last step, as I said before, we need to test our model. So here we want to compare the predicted class of our document versus the actual class of our document. And in red here, we have the number of documents that are misclassified. And we want to learn from the mistakes that were done, reincorporate them in the train set, retrain our model in order to have more accurate probabilities and hence be able to classify more correctly our documents. So that's all I have for today. Thank you very much. Thank you.